Bipolar junction transistors, or BJTs for short. In this presentation, we're going to look at how a bipolar junction transistor operates, some basic calculations around the circuit parameters of a BJT, and some ratings of the equipment. Like most electronic components, bipolar junction transistors, or BJTs, are manufactured from silicon carbide. The layering and use of P&N type silicon is similar to a standard diode. If we see on the left here, there's a standard diode with P&N type material. On the right is two different types of BJTs. And the two different types of BJTs use different amounts of P and N type silicon. So one's called a PNP and the other's called an NPN. A BJT shares some of the characteristics of a standard diode. It has PN junctions and is polarity sensitive. A BJT can control a load in a similar manner as a relay, as in on and off. It can operate as a variable control device. It has two distinct circuits, and it comes in two different varieties. So you can see here on the left, we have a NPN type, and over here on the right, we have a PNP. The difference between these two symbols, as we see here, is the direction of current flow. So, depending on the polarity that I have connected or that I have need of, I might choose to use a PNP or an NPN, depending on the application. But for their overall purpose and use, they do the same thing. This is a transistor schematic symbol, and what we're going to be looking at is the interaction between the base, the collector, and the emitter. The direction of arrow, as usual, indicates the direction of current, and yes, that is conventional current that we're showing. Now, a transistor has two distinct circuits, a base circuit and a power circuit. The two circuits share a single path on the emitter end of the component. Current traveling into the base terminal controls the value of current that would flow from the collector to the emitter terminal of the power circuit. For a BJT to conduct current from C to E, current must be traveling into the base terminal. There must be at least 0.7 volts from B to E, and the correct polarity must be applied to the terminals. Current traveling into the collector and out of the emitter terminals is then going to be represented as a basic IB plus IC equals IE. So the base current, we can see here, very small, is going to control or allow current to flow from C to E, and the E value here is obviously the combined value of both the collector and the base current. The base current magnitude controls the value of current that flows from collector to emitter. If the base current increases, the current from C to E will increase. If the base current decreases, the value C to E will decrease. How much current C to E changes is dependent on the amplification of the BJT. Amplification is known as gain and represented by the letter or the word beta, and it's calculated by IC divided by IB, and that gives us a numeric value here, beta, which represents the amplification of the transistor. Beta for this particular installation would be 500 milliamps divided by 3 milliamps, so an amplification of 166.6. This number can be used to create a ratio, which means if the base is increased by 1 milliamp, the collector will increase by 166.6 milliamps. Or we can use a reverse way of calculating and say beta is equal to IC over IB. So we've got 166.6 equals IC over IB, and then you can adjust the equation and say 166.6 times IB is equal to the collector current. So if you know what the base or the beta is, and you know what the base current is, then you can determine how much current is permitted to flow here, IC. Now, if we take a look at these four different diagrams, if it's the same transistor with 166.6 beta, then that means that I can take that and multiply it by the base to determine the collector current. And then I can add the collector and base current to determine the emitter current. So let's do the far left one with the 1.2 milliamps. I've got 166.6 times base current. That should give me the collector current. And then I can take base and collector, and that should give me the emitter current. So that gives me 199.9 milliamps for the collector and 201.12 milliamps for the emitter. If we look at the next one over at 3.5 milliamps, I'm expecting a pretty large increase in the collector and emitter currents. So again, taking the 3.5 times 166.6, that gives me 583.1 milliamps. And if I take these two and add them together, I get 586.6 milliamps. If we look at this one down here, 2.2 times 166.6, that gives me 366.5 milliamps. If I take these two and add them together, 368.7 milliamps. And finally, may as well do this one, 6 milliamps times 166.6 gives me a behemoth 999.6 milliamps. I add those two together and I get just over 1,000 milliamps. A BJT can only increase current C to E up to a point called saturation. Beyond this value, the base current will have no ability to increase the collector current according to the gain. So increasing base current beyond saturation levels can lead to transistor destruction. So let's say with this same example of transistor, 6 milliamps, that's almost at the top of saturation. And according to, the data plate for this transistor, this is reached, that is saturation, 1082.9 milliamps. And any further increase here will not cause an increase in the collector current. Now, it will cause a slight increase in the emitter current, but that's simply because the base plus the collector current equals the emitter current. So, yes, it has gone up a little bit, but increasing this beyond saturation levels means that, likely the transistor is going to be damaged. So when you exceed those values, the current is too high, and you end up destroying the item. Now, resistors are sized to ensure the transistor base current does not exceed the maximum saturation value. A BJT requires at least 0.7 volts across terminals B to E for current to flow. If the voltage is lower, no current will flow from the emitter terminal. So here we can see 0.3, 0.7, there we go. We got current flowing through the base terminal, and that's what allows the C to E current. The transistor will only conduct while the base terminal is energized and base current flows. If there is no base current flowing into the transistor, there is no current flowing from the collector to the emitter terminals. Transistors usually share two separate sources. The sources may be the same voltage or different. We can see here the base current and the collector current here in two different areas. Now the base current controls the current flowing from C to E. So let's see what it looks like in an operational circuit. Now transistors can be used for on-off control like a relay or variable load control like a light dimmer. So let's start with an on-off control. Here's an on-off. I've got a resistor that's sized to allow for saturation level of base current in my transistor. I've got a load on the far right-hand side. It's a 12-volt source we've got there. I've got a 1-volt source here. There's a common connection between the two. And I've got a negative connected down to the emitter, positive connected to the collector, and positive connected to the base. And this is simply a switch. Right now it's open. Let's close the switch. Right now, C to E acts as an open switch. So that means C to E here, that is open and the light is off. So let's investigate a few of the voltages. I'd have 12 volts because it's a 12-volt source. Across the open, this voltage would be 0. And right now, because the switch is off, I have 0 volts from B to E. Now, if I close the switch, things are going to change. So now what I have is 0.1 volts from C to E. And that means that I have voltage that would be applied to my load. So let's look at each value. When I close the switch, I have at least 0.7 volts B to E. That means I'm going to have base current that's going to flow within the system. That base current will allow current to flow C to E. And of course, that's going to energize my load. Let's look at a transistor with variable operation. This is a variable resistor or a slider switch, so it's going to operate a little bit different. Again, I got my load, 12 volts and 1-volt source. Right now it's set at maximum, which means there's no current flowing into the base terminal. As I move the switch over, we're going to see that a little bit of current flows into the base terminal, and that's going to affect the voltage that is permitted from C to E. It's not permitting 100% of the current flow through, and so my light is like dimly lit. If I move this all the way over, I have more base current, and more base current allows more current to flow C to E, and that makes my load turn on brighter. There are many different types of transistors out there in the marketplace. Some of them are canister types, some are more sort of circuit board rated, very small. And it kind of depends on the application that you're looking for, but they're not intended to carry significant current. There's a data sheet for a basic transistor. We can see it is an NPN type transistor, and so very small terminals, and the value of voltage and current are usually listed in milliamps and milliwatts of power dissipation. So in closing, let's remember, a BJT can control a load in a similar manner as a relay, on or off, or it can control a load as a variable control. It has two distinct circuits, and it comes in two different varieties.